ask a simple question. Which is the stronger base? Stronger base when we take a look at two different molecules versus okay, both of these have a negative charge. They can act as a base. And so we want to figure out which one is the stronger base. The first thing that you need to do, step one, is you need to look at the conjugate acid. So can you look at that conjugate base and draw what the conjugate acid would look like? Now, what's the definition of an acid? Something that donates a proton. So all we have to do, class, is add a proton to where that negative charge is. So the conjugate acid would look like this. Do you see how I just added that hydrogen right there? You can't see it. Now you can see it. We just added that hydrogen. So then what would the conjugate base of that nitrogen species look like? You would use one of those lone pairs to draw the next hydrogen. Okay? So that's your first step when the question is asking base strength. Look at the conjugate acids. Now, I've asked you guys in the videos to memorize some common pKa's. What would the pKa be for that alkyne? About 25. And then the pKa of an amine? 38. Okay, so now if we have those memorized, we can look at the conjugate acids and ask ourselves, which of those acids is the stronger acid? The one on the left. Why is the one on the left the stronger acid? Smaller pKa. Perfect. So we've identified that this is the stronger acid. And so stronger the acid means that it's the conjugate base of the acid is weak. Okay? And so that conjugate base is going to be weak because it comes from a strong acid. So by default, that makes this guy the stronger base. Or you could say, hey, that's the weaker acid. So that makes that its conjugate base the stronger base. You could view it like that if you'd like. But that's how you do it. Okay? If you know your pKa's. So let's apply this principle. What if we had a ketone versus an alcohol? Okay? And I ask you the same question. Which one is the stronger base? What's the first step, class? Draw the conjugate acid. So what would that look like? Where would I put a hydrogen? Could I put a hydrogen right here? No, you'd create a Texas carbon. But we know that a ketone has two lone pairs, and so we could use one lone pair there to put the proton on that oxygen atom right there. Okay, so we have to think about this in terms of the octet rule and whatnot. Where could a hydrogen possibly go that doesn't violate the octet? And then we would see that we could tack on a hydrogen right here, like that. Now what happens to that oxygen? It's going to be positively charged, right? Now in this particular example, we would kind of do the same thing if we know the pKa's. But these are structures that I did not have you memorize. So I would have to give you the pKa's for this particular problem at this moment in time. But come exam day, if I give you something that's not if I give you structures that isn't one of the ones that you're supposed to memorize, you still will be able to figure this out without me giving you the pKa's. And that's what next class period's about, or the next set of videos. How do you figure out what's the stronger acid or a stronger base when you don't have a pKa? And I use something called the cardinal rule. And the cardinal rule is not found in your textbook. Your textbook uses a different method. What's the method called in the textbook for Orgo? Yeah, Orgo. I don't even know what that stands for, really. Well, I can figure it out, but pick which one you want to use. Okay? I do cardinal rules. That's what I like using. And the video will teach you how to use that. So that's where you're going to get to. If you don't have the pKa's, you're going to use the Orgo or the cardinal rule to figure it out. But we're not there yet. So I would have to give you these values, and that's a negative 7.3, and that's a negative 2.4, like that. So which is the stronger acid? That's the stronger acid. That's the weaker acid. So if that's the weaker acid, we can say that would have to be the stronger base. So you see how it was the same process, it's just the molecule looks different. So if your study strategy is to just memorize molecules, then that's not how you study. You see the principles and the process that I use. That's what you have to learn and do well. Okay. Now, once we can identify weaker and stronger bases and acids, we can apply that to a situation when we come to like equilibrium. What if I have tert-butoxide plus water? Well, let's expand out the water so it's a little bit easier to see. Okay, so if we have that, how's the reaction going to proceed? What's going to happen? What do the products look like? Well, more often than not, when you have something that's negatively charged, that's going to act as the base. And then water, you already know from all your years of chemistry that can act as an acid. Okay. Water's tricky though. It can act as an acid and a base, as you'll see as we progress. But either way, in this particular situation, this is how it's going to be. Water will act as the acid, and the tert-butoxide right there will act as the base. So mechanistically, how does that work? The acid has to what? Donate its proton. Give it up. But how it does that is very, very important. Okay? This is the mechanism. We take one of the lone pairs and it comes and snatches that hydrogen. It forms a bond with that oxygen and the hydrogen. Now at that moment in time, that hydrogen atom right here has this bond and the newly formed bond with the oxygen atom. So it has two bonds. That's not good. So what we have to do is break the oxygen-hydrogen bond and stick the two electrons within that bond on the oxygen. So now we have something that looks like this. We just formed this oxygen-hydrogen bond. So this hydrogen is now that guy. Now what's the formal charge going to be on this tert-butoxide? It's now tert-butanol. That oxygen atom is now neutral. Now what happened here? We have this piece right here. This oxygen atom already has two lone pairs on it. So when we come over here on the product side, how many lone pairs does the oxygen have? It has 3 lone pairs. That would make that a negative charge. Okay, that's acid-base chemistry. And this is very, very important, guys. So many students do this, and I'm telling you, it's 100% wrong. Don't do it. I know what you're thinking, but mechanism arrows show the flow of electrons. We take this lone pair, and it forms a bond with that hydrogen. And that's what the arrow is showing, where those electrons go, what bonds it forms. Far too many students will just say, hey, this hydrogen's going to pop on and go over there. Okay? That's what they do. They say the hydrogen's flopping off over to that other oxygen. That is not a mechanism arrow. That doesn't happen. Because let's think about it. I just said these mechanism arrows show the flow of electrons. Do you see that this right here, the start of my arrow starts where there's electrons. But in this green arrow, where's the electrons around this hydrogen? Where's the lone pairs? There's nothing. So there's no electrons that can move over here. So if you ever feel the urge to draw a hydrogen and drawing it somewhere, it's always wrong. Just don't do it. You have to think, where are the electrons? Lone pairs, pi bonds, and watch those flow. Now that we've done the correct mechanism here, what is our conjugate acid on this side, and what is our conjugate base? Well, we track it. If this is the terbutoxide, it turned into terbutanol. And so if we start with the base, then that has to be the conjugate acid. And then we see our acid, which is water. What does the water turn into? Hydroxide. So that has to be the conjugate base because it's a pair. An acid-base pair. So that's how we identify the conjugate acid and the conjugate base. Because what happens, do you see this arrow those arrows right there? That's equilibrium. So what does that mean? That these species over here can go in the reverse direction and go back. That's what equilibrium talks about. So how does that happen mechanistically? We use a lone pair. It comes, grabs the proton. Can the proton form two bonds? Nope. So we have to break that. And now these species turn into those two. Do you see that? So when I ask you to draw the mechanism, I'll specify draw the mechanism in the forward direction or the reverse direction. But you need to see the flow of the electrons and where the hydrogens go. So this hydrogen here, where did it go? Back to the water. Formed the water. Okay. After that whole exercise of being able to figure out where you're conjugate the species and what they are, now we can, if you have the pKa's memorized, now you just find the acids and write the pKa's below them. Okay, so the pK of water, we could roughly say 16, but more accurately it's 15.7. And then, do I have a pKa for this species? No, that's a base. I said a pKa, which stands for acid. So what's the pKa of this alcohol right there? I told you what, 16-ish would be the average? 15 to 16. Okay, 15 to 16, it's a range, it doesn't matter. As long as you're in that ballpark, then you're going to be okay. But it's more complicated than that. In this particular situation, the pKa is 18. Okay? Do you need to remember that? No. It's an alcohol, 16-ish. Okay? That's all you have to remember. So the question that we're trying to figure out is at equilibrium, once that's been reached, which side is favored? Are products favored or reactants favored? Okay? So the way that we do that is we take a look at the pKa's. Okay? And we ask ourselves, where is, let's see. What you want to do is find the weaker acid. Where's the weaker acid? On the product side, it's over here. So equilibrium is going to favor in the direction of where the weaker acid is found. And the weaker acid in this situation is found on the product side. So when we come to equilibrium, when we put these reagents together and dump them in, where's it going to end up? And it's going to be favored to the right side, or the product side. Okay? But then we can ask another question. If it's favored to the right, how far or how favored to the right is it? Is it favored to the right just by a little bit, or by like magnitude? Like it's just all to the right. Okay, so that's the next question that we want to answer. Like put a value to it. Is it 100 times to the right or not? And the way that we do that is we take the pKa's that you know and you just subtract them. So 18 minus 15.7. And you're going to get a value of 2.3. Now we have to remember that pKa's are logarithmic. They're logs. So it's not 2.3 times favored to the right. It is 10 raised to 2.3 times to the right. And what does 10 raised to 2.3 equal? Well, let's just simplify it. Let's 10 raised to the 2. That equals 100. So once this reaction comes to equilibrium, it is favored to the product sides by 100 times. And so what that means is for every 100 molecules of this conjugate acid, we're going to have 1 molecule of the conjugate base. That's 100 times, is it not? But 100 times favored to the right. Let's have you guys do one all on your own. Okay? I'll give you like a few minutes. Well, no, what I'll do, I'll draw this problem and you guys can solve it over the weekend. We'll do another assignment that's a little bit more important. Well, I think it's more important. But here's the question. Okay, if we take butane plus hydroxide, okay? I want you to follow the same procedure that I did for the problem that we just worked on. What are the products? Identify the conjugate base and the conjugate acid. Which one's the acid? Which one's the base? And tell me at equilibrium which side is favored and by how much. So I want you guys to do that over the weekend and be ready to give me the answer in class on Tuesday. So what we're going to do now is there is an assignment that you're going to find in the module. It's called Acids Part 1. I need you to start working on that. You will upload a picture of your work to that assignment link by the end of class. But when we have about 10 minutes left of class, I'm going to do something else. Okay? So start working on that as a group. Submit it by the end of class, and then we will do something else.